5.4, solving special systems of linear equations. So first of all, this one on the left, this has one solution over here. That's the type of system that we've been solving so far, and that has one solution. So graphically, when we graph the two lines, they intersect at one point, and that's your one solution. Now, over here in the middle, no solutions would look something like this. We have two lines, but they're never ever going to touch, so they're never going to have an intersection, therefore no solution. And in this case, the lines are parallel. And then last but not least, infinitely many solutions. If you look at this graph, it looks like there's only one line. There's actually two lines there, or maybe even three or four, but the lines are exactly the same. So they're actually lying on top of each other, so all of the solutions will work. Let's take a look at what this actually looks like if we were to solve it. So number one, solve each system by elimination. Check your solution. Now, keep in mind if we're using elimination, we need the x's to line up, we need the y's to line up, and then we need the constants to line up. So far so good. But then we need either the x's or the y's to have an opposite coefficient. Right now, I've got a 1 and a 2. I've got a 1 and a 2. Those are not opposite. So in order to get an opposite coefficient, I'm actually going to multiply my first one by a negative 2 so that this becomes a negative 2, which is the opposite of positive 2. I'm going to draw my arrow and distribute. Negative 2x minus 2y equals negative 6. Then I'm going to leave my second one the same, which is just a 2x plus a 2y equals 6. And then we're going to add. Now, when we add, a negative 2x plus a 2x is 0x. A negative 2y plus a 2y is 0y. So right now I'm sitting with a complete 0 on the left equals negative 6 plus 6 is 0 on the right. Well, I'm looking at that statement and all of my variables are gone. So 0 equals 0 is true. So if I get down to a true statement, that means infinite solutions, meaning any point that I pick that satisfies one of these lines will satisfy the other line. Letter B, y equals negative x plus 3. Now, once again, we're supposed to solve this by elimination, but when I look at this, elimination is not our easiest pick here, so I'm actually not going to do it. This one up here is already solved for y, and it says y equals. So in that case, I'm just going to take this, and I'm going to use substitution, and I'm going to substitute it in for that y. So that's going to give me 2x plus 2 times y, which we're substituting negative x plus 3 equals 4. Then I'm going to solve this, so I'm going to leave the 2x. Then I'm going to distribute 2 times negative x is negative 2x. 2 times 3 is plus 6 equals 4. Then I'm going to take my 2x and my negative 2x, and those are going to combine to 0. They're going to cancel each other out, and then we're going to be left with 6 equals 4. Now, when I look at 6 equals 4, that statement is false. That's not true, and all my variables are gone, which this is going to mean no solution. So these two lines, if we were going to graph them, are actually parallel. They would both have the same slope. This is y equals mx plus b, so the slope here is negative 1. So both of these would have a slope of negative 1. Letter C, x plus y equals 3, x plus 2y equals 4. On this one, my x's are already stacked, my y's are already stacked, my constants are already stacked, so I am going to use elimination. I'm looking at my x's because they both have a coefficient of 1. The only thing I'm going to change is I'm going to multiply this first one by a negative, so that they're opposite, so that this one becomes a negative 1 and this one's a positive 1, and then we can use elimination. Distribute This is negative x minus y equals negative 3. Then I'm just going to bring this one along. X plus 2y equals 4. And then we're going to add. When I add, a negative x plus an x is 0. A negative y plus a 2y is a positive y equals negative 3 plus 4 is 1. Well, at this point, I still have a variable, and this actually says y equals 1, so I'm going to take it and substitute it back in. I'm going to choose to substitute it in the first one. Again, it does not matter. I'm just choosing that. So I'm going to have x plus y, which is 1, equals 3. Subtract 1, x equals 2. So our final answer here would be 2, 1, which this would just be one solution. And that one solution is at 2, 1. So if we were to graph these, they would intersect at 2, 1 in one location on the graph. Letter D. This one, once again, I know it says elimination, but this is not set up for elimination. This is actually set up for substitution. So this is y equals negative 10x plus 2. So I'm going to take this and I'm going to substitute it in for y. So I'm going to have 10x plus negative 10x plus 2 equals 10. That's going to be 10x minus 10x plus 2. I'm essentially kind of just dropping the parentheses here and letting that plus negative take over as a minus. Then I'm going to combine like terms. So 10x minus 10x is 0. So now I have 2 equals 10. My variables are gone, and that is false. 2 does not equal 10. So this is going to tell me no solution. Now, real quick before we move on, I'm just going to look at that one other way. If I go back up, I have y equals negative 10x plus 2. Well, if I solve my second equation here for y, I could subtract 10x, I could subtract 10x. That would get me y equals negative 10x plus 10. And now I'm going to look at those two equations. Both of those equations, if I look really carefully, have a slope of negative 10. Which means on the graph, if I were to graph them, a slope of negative 10 maybe looks something like this. But this one has a y-intercept of 2, so maybe like right there. And this one has a y-intercept of 10, so maybe like right there. But they both have the same slope. So if they have the same slope, they're going to be parallel, but they have different y-intercepts. So graphically, no solution because they're parallel and they're never going to hit each other.